Hermitian operator. What is this Hermitian operator? We already discussed what is a Hermitian matrix. You are familiar with the Hermitian matrix. That is, here in the sense of Hermitian operator, if a dagger is equal to A, where A are operators. If it satisfies this condition, then we can say it is a Hermitian operator, or we can call it as a self-adjoint. So in Dirac notation, bra psi ket A psi. So I can expand this, that is I can take this operator A outside this ket, that is bra psi operator A ket psi. And suppose bra A psi ket psi. So I told you how we can take a parameter from inside the bra. That is, when we are taking its from inside the bra, we have to take its dagger, right? That is, here we get bra psi A dagger psi. And if these two are equal, then we can say the operator is a Hermitian operator. That means in integral notation, that is integral psi star A psi dato is equal to integral A psi or star psi dato. So if this integral will satisfy the values, then also we can say this is a Hermitian operator. That is, if it satisfies, this is called the A is Hermitian operator. Okay. And suppose if A dagger is not equal to A, it is minus A, then we can say it is a anti-Hermitian operator. Okay, now let us check some examples. First example, d by dx dagger. So when you are solving for d by dx dagger, you will get the result as minus d by dx. So here see, there is a minus sign came additionally, so it is a anti-Hermitian. Second one, del dagger. See, we know what is del operator. That is I dou by dou x plus j dou by dou y plus k dou by dou z. So this is nothing but d by dx, d by dy, right? So we know what is d by dx dagger, that is minus dx. Okay. Therefore, this one will be equal to minus del. So this one is also anti-Hermitian. Now the third example, that is I d by dx dagger. So earlier when we were discussing the properties, I told you how we can take this dagger into this bracket time. So first you have to take d by dx dagger, because these are operators. So order is very, very important. Okay. So d by dx dagger, I dagger. So what is d by dx dagger? We know that is minus d by dx into I dagger is conjugate transpose of I is minus I, right? That is into minus I. So we get I d by dx. See, we got same value, that is this is a Hermitian operator. Now we can take our momentum operator, that is minus I h cross dou by dou x dagger. What we will get? Again, we have to take d by dx dagger, and here h cross is a constant value, so you can take at any position, no problems. Okay, into minus I dagger, that is minus 1 into, now we have to take a dagger of I, that is complex conjugate of I, that is minus I. So that is equal to, see, a dagger of d by dx is minus d by dx into h cross into minus I, that is I. So what we obtain? We obtain minus I h cross dou by dou x. See, we got the same value. That is, this is also Hermitian operator. All the quantum mechanical operators are Hermitian. Okay, if you take a dagger of a momentum operator, or if you take a dagger of position operator, or if you take dagger of energy operator, you will get the same value, because all these operators in quantum mechanics are Hermitian operators. So fifth one, because then you will get much more idea about the operators. That is d by dx all square. We have to check whether this d by dx all square is a Hermitian operator or not. So that is the question. So what you have to do? You have to take its dagger, right? So that is equal to, here one problem is there, that is d by dx square doesn't means d square by dx square, because these are operator. Okay, so square means d by dx into d by dx. That is, if there is some operator that is like d by dx square operating on some operator, that doesn't equal to d square psi by dx square. Okay, this is not in the case of operator algebra. This is our algebra, but in the case of operator algebra, d by dx all square means, suppose if it's operating on some certain wave function psi, that means d by dx into d by dx of psi. Okay, so first we have to evaluate this d by dx over psi, then we have to evaluate this d by dx over this psi, then only we can take this one. Okay, here in the case it is same, both are same, but when operator operates on some state vector, then this is the procedure. We cannot take direct square. Okay, or we can say okay, so okay, sufficient. I think is sufficient, right? Now let us discuss, okay, this one. So d by dx dagger, this is we have to find out. So first we have to take dagger of this state, that is d by dx dagger into d by dx dagger. That is, we know d by dx dagger is equal to minus. So here also we get minus. So minus minus. So finally we will get d by dx square. Okay, so this one is also a Hermitian operator. Now the sixth one, that is del square dagger. See, this is nothing but d by dx plus d by dy dz. So additional terms also will come, that only the difference. So this one also will behave as the above case. That is, again above we got it is a Hermitian operator. So this one is also Hermitian operator, that is del square. Seventh one. Suppose if A and B are Hermitian operators, then we have to check first option, A dagger plus B dagger. Is this one is Hermitian or not? That is the question. So what do you have to take? That is A dagger, sorry, A cap plus B cap dagger is equal to, we know it is addition only, so that is A cap dagger plus B cap dagger. And it is specified A and B are Hermitian, so A cap dagger will be equal to A plus B cap dagger is equal to B. So this is a Hermitian operator. Next one, A cap minus B cap. I think this one you will solve. Okay, do it as a work. Okay, see, because nothing is the same as above, right? Now third one, I into A plus B. Now we have to check is this is a Hermitian operator or not. So what we have to do? We have to take I A plus B dagger. So we get A plus B dagger into I dagger, right? That is, we can expand, that is A cap dagger plus B cap dagger into I dagger is equal to minus I. That is complex conjugate. Dagger is complex conjugate. So it is a complex value. Sorry, dagger is complex conjugate transpose of a conjugate transpose. The dagger is conjugate transpose. Okay, so first you have to take the conjugate of that term, then we have to take transpose. So transpose in the sense of if it is a matrix, then we have to change row into column, column into row. Okay, so here it is a complex function. So conjugate, when we are taking conjugate, we will get minus. So minus I, right? So this is equal to, we know A and B are Hermitian operator. So this will be equal to minus I A plus B. So this is anti-Hermitian because there is a minus sign. Okay. Another one, that is B. That is I A cap minus B cap. I think you can do it. It's a simple one. So the final answer is, it is anti-Hermitian. Okay, do it. The same procedure, right? Now let us discuss some important rules. Rule number 1. That is, a statement is the product of two Hermitian operator is also Hermitian only when they commute each other. Maybe you have some doubt what is all these things. Don't worry, I'll tell you. Okay, so we can prove this rule. So let us consider A and B are two Hermitian operators. Okay, that means if we take dagger of A, we will get A, and if we take dagger of B operator, we will get B operator. Okay, that is the condition. So now what we have to do? The product of two Hermitian operators. So these are two Hermitian operator. Now we can take its product, that is A, B. Okay, is also Hermitian. So we have to check whether this is Hermitian. To find out whether it is Hermitian, we have to take dagger, right? So this is equal to B dagger, A dagger. And we know B and A are Hermitian operator. So this is equal to B A. See, here the order is very important. See, here it is A, B, but after taking the dagger, the order is B, A. That is, if there is a operator psi, a vector psi, then this B will first act on it. See here, this is AB. That is, order is very important. So this operator is AB. Here this operator is BA. These two operators are not equal. So now we can check the other condition, that is operator is also Hermitian, that is these are two different operators. So we didn't satisfy this condition of Hermitian operator, that is A dagger should be equal to A. Okay, here AB is a one type of operator, but what we got BA. So this is not a equal. AB is not equal to BA. So we can check the other condition, that is also Hermitian, that is this product is also Hermitian only when they commute with each other. That is, if BA, this BA is equal to AB, so we can write AB dagger is equal to, we got BA, and if BA is equal to AB, that is they commute each other, the order is not a problem, then this is equal to AB. So we got A dagger, B dagger. So we got A, B or dagger is equal to AB. So now it is a Hermitian operator, right? So this is the proof. That is, here AB should be equal to 0. Then only this will satisfy. Or in other sense, we can say commutator operator is equal to 0 means they commute each other. And let us discuss an example. I told you all the quantum mechanical operators are Hermitian operators. So position operator and momentum operator are Hermitian operators. Right, now we can take its product, that is x cap p x cap, and we are checking whether the product is also a Hermitian operator. So we have to take dagger, so we will get px dagger x dagger. So we know these are Hermitian operator, therefore px dagger is equal to px and the x dagger is equal to x. See, here this operator is xpx, right? Here this operator is pxx. Both are different. In an earlier problem, we got some 2 into 2ih cross into 2xp plus, sorry, xp plus px cap x cap in an earlier problem. So at that time, we didn't added these two terms, right? The reason is these two are different operators. So the product is not a Hermitian operator. The reason is we know x px is equal to ih cross. It is not equal to 0. Okay, it is not commute each other. Therefore, these two operator will not. So the product of these two operators is not a Hermitian operator, and it will be, any operator will be, a product of any operator will be a Hermitian operator only if it satisfies commutator operator. Commutator of it is equal to 0. Okay. The next rule, rule number 2. The commutator of two Hermitian operator is also Hermitian only when they commute each other. What does it mean? I tell you, it's a proof. How we can prove this? That is, the first condition is the commutator of two Hermitian operator. So this is the commutator of two Hermitian operator. I am taking A and B are as Hermitian operator. So this is the commutator of two Hermitian operator, and this is equal to, and this is also Hermitian. That means this is equal to A B, commutator A B. Okay, because this entire term is a Hermitian. So when we are taking the dagger, we will get that entire term, right? Now, how we can check this? We know we can take this dagger inside this commutator. So when we are taking that inside the commutator, we will get B dagger A dagger. That is equal to AB. And here it is specified the commutator of two Hermitian. So this A and B are Hermitian operators. That means A is equal to A dagger, and B is also equal to, B is also equal to B dagger. Okay, so we can replace this B dagger as B and A dagger by A. So BA is equal to AB. See, the order is different, so we cannot say these two are same. So we can check, so we can make the order in a same fashion. So we have to interchange this A and the B. So when we are interchanging two components inside a commutator operator, there will be a minus sign. So this will be minus A B. That is equal to commutator AB. See, this is like minus x is equal to x. Is there any chance for minus value is equal to a positive value? No, right? That is, only chance is x should be equal to 0, right? In the same way, here this commutator, that is A, B, should be equal to 0. Then only the above rule will satisfy. That is, this rule will satisfy. So that is, commutator A, B should be equal to 0. That is, they commute each other. That is AB. What is this value? That is AB minus BA is equal to 0. Okay, that is why we are telling they commute each other. Okay. Then only we can say they commute each other. Okay. And the other rules of Hermitian operator are rule 3. The eigenvectors of a Hermitian operator corresponding to distinct eigenvalues are orthogonal. What is the meaning of this one? I think I tell you, a Hamiltonian operator is there, that is energy operator is there, and it is acting on certain state psi. Then it will give an energy value and that wave function, right? Suppose this wave function is psi 1, and when operating this Hamiltonian operator, we got energy E1 and wave function psi 1. And this Hamiltonian operator operates on another state psi 2. So we will got another energy E2 psi 2. See here, this energy eigenvalues or any eigenvalue, here it is energy eigenvalue because operator is energy operator. So these eigenvalues are distinct, E1 and E2. So their corresponding eigenvector, that is psi 1 and the psi 2. So if you take bra psi 1 get psi 2, then you will get this is equal to 0. That is, they are orthogonal. That means earlier we discussed about 1D box and all, right? So if we take first ground state wave function psi 1 and the first excited state psi 2. These two vector, that is, I told you we are representing all these vectors in a Hilbert space. So in Hilbert space, this is psi 1, okay, this is psi 2. So these vectors represent the state of particle in 1D box. So this is our Hilbert space. Okay, like our Cartesian system, that is 3D space. X, Y, Z. We represent the particle position, momentum, etc. by some vectors. So similarly, here we represent, in quantum mechanics, we represent the state of the particle by vectors in Hilbert space. So these two vectors in Hilbert space should be orthogonal. Here we know in Cartesian coordinate system or 3D space, if two vectors are there, suppose X is there and Y is there, we know this two are orthogonal to each other. Okay, in a similar fashion in Hilbert space, we cannot say it is a 3D space, it is a n-dimensional space. Okay, in that space, Hilbert space, these vectors are different if, or orthogonal if the corresponding energy eigenvalues are different. Okay. Rule number 4. That is, eigenvalues of Hermitian operator are real. So we know Hermitian operator is position operator is a Hermitian operator. And the momentum operator is also a Hermitian operator. Energy operator is also a Hermitian operator. If this operator operates on some state vector, we will get a eigenvalue. That eigenvalue is a real eigenvalue, right? We already seen many examples. And if another case is also there, the eigenvalues of anti-Hermitian operator are purely imaginary or 0. Okay, so these are anti-Hermitian operator, then their eigenvalues are purely imaginary or 0. Okay, so remember all these things. In the earlier class, I told you the operator algebra is very different from our algebra. I told you in our algebra, a plus b all square, we know it is equal to a square plus 2ab plus b square. But if you are considering this case in operator algebra, then it will be square will be equal to a cap plus b cap into a cap plus b cap. So that is equal to, we can multiply each of this term. So we get a cap plus a cap, b cap plus b cap, a cap plus b cap, b cap. See, these two terms we can add like this because AB operator and BA operator are different. And another example also I discussed, that is AB square. So AB square, we know in our algebra it is a square b square. But in operator algebra, AB square, that is a cap b cap square, is equal to a cap b cap into a cap b cap. That is a b a b. So if there is some operator on right hand side, then first this b operator will act on this one. So we will get a value, right? On that value, this operator will act, a operator will act. Then on that value, b operator will act, and on that value, this a operator will act. It is different from this case. Here, what is the situation? It is like a B, B. See, this one and this one are very, very different. So, this is our operator algebra. Similarly, I told you another case also, that is e raised to a, e raised to b. In our algebra, it is e raised to a plus b. We can write this like this, right? But if it is, these are operators, that is e raised to a cap, e raised to b cap, then this is not equal to this value. Then what is this value? That is the question. That is what we are going to find out. Initially, I tell you what is the answer. That is e raised to a, e raised to b cap will be equal to e raised to a cap plus b cap plus commutator a cap b cap by 2. So this will be e raised to a cap, e raised to b cap in operator algebra. Okay, not this one. Okay. Now let us derive that value. Okay, e raised to a, e raised to b cap equal to what? That is what we have to find out. So let us consider a function. It is a function of t that is equal to e raised to a t, e raised to bt, where t is some parameter. Now I am going to take derivative of this function, that is df of t with respect to time, that is dt. So what we will get? We will get, so we have to take a derivative of first time, that is derivative of this one, right? So derivative of e raised to at is e raised to at itself, and the derivative of at with respect to t is a. So a into e raised to at, e raised to bt. Now we have to take derivative of second time, that is plus. Now we have to take derivative of second time, that is e raised to a t. Derivative of second time we will get b cap e raised to bt. Now that is equal to a cap e raised to a cap t e raised to b cap t plus e raised to a cap t b cap into, I am introducing one term here, that is I into e raised to bt, where I is identity operator, and that is equal to e raised to minus at into e raised to at. So this operator will cancels each other, and we will get value 1, that is identity. Okay, so I can substitute this I here. That is, this is equal to df of t by dt is equal to a cap e raised to a cap t e raised to b cap t plus e raised to a cap t b cap. I is e raised to minus a cap t e raised to a cap t into e raised to b cap t. So this term is a common term, right? So I can rearrange df of t by dt is equal to, I am taking this common term outside the outside. So I will get, this is equal to a plus e raised to a cap t b e raised to minus a cap t into e raised to a cap t into e raised to b cap t, right? Where this term is nothing but our f of t, that is, this is equal to a cap plus e raised to a cap t b e raised to minus a cap t into f of t. Here we have to evaluate this term. That is the next step. What is the value of this term? So to evaluate this term, I am taking, let us consider commutator e raised to a cap t b cap. Okay, so what is this commutator? We know this is a function of a and b. So commutator a b is our trick, right? Into this is a e raised to a t is a function of a operator. So we have to take derivative of e raised to a t time. That is, we get t into e raised to a t. That is derivative with respect to the operator, right? Now we can expand our commutator operator. That is, we now e raised to a cap t into b cap minus b cap into e raised to a cap t. That is equal to t into commutator a cap b cap into e raised to a t. Here I can take this t at any position because it is not an operator, but I can change the position of operators. So here, see, this one is e raised to atb. First I am going to find out what is this value of e raised to atb. So this is e raised to atb. So I am taking this term to RHS of this equation. So we will get e raised to a cap t b cap is equal to t into commutator a cap b cap e raised to a cap t plus b cap e raised to a cap t. Here our object is to find out this value, right? So we got e raised to a t b. Now we have to multiply that term with the e raised to minus a t, right? That is, we have to e raised to a cap t b cap into, we have to multiply this term, this entire term, by e raised to minus a cap t. That is equal to t into commutator ab e raised to a cap t, because this function is on right hand side, so we have to multiply on right hand side of this equation, right? That is e raised to minus a cap t plus b cap e raised to a cap t into e raised to minus a cap t. That is equal to, see, e raised to a cap t, and this one will be equal to 1, and this one also become equal to 1. That is, we get t into a cap b plus b. So we got the value of e raised to a cap t b e raised to minus a cap t. Now we have to substitute this value in our earlier equation. That is, what is the earlier equation? That is, df by dt is equal to a cap plus, see, now we have to substitute this value, that is t into a cap b cap plus b cap into f of t. Now I am going to do one thing. When I am changing this position to here, b position to here, and here this is df by dt, and here there is f of t. So I am taking this f of t to left hand side, and I am taking this t to right hand side. That is, I am making it a variable separable form. That is, df by f is equal to a cap plus b cap plus t into a cap b cap into dt, right? Okay. Now what we have to find out? We have to find out the function f. That is, function f is defined as e raised to at e raised to bt. So this is what we have to evaluate. So to find out the f from this equation, we have to take integration. Okay, so on integrating this function df by f, what we will get? We will get this is equal to log f. That is, log f is equal to, so we have to integrate this term with respect to dt, right? So we will get a cap t plus b cap t plus integral of t, that is t square by 2 into a b. Now this is a log f. Therefore, in order to find out f, we have to take this exponential on both sides. So if you're taking exponential of the log f, we will get f, that is equal to e raised to a cap t plus b cap t plus t square by 2 into a cap b cap. That is, we know f is equal to e raised to a t, e raised to bt, that is e raised to a cap t, e raised to b cap t is equal to e raised to a cap t plus b cap t plus t square by 2 commutator a cap b cap. So this is the answer. This is general solution, right? So see, this is very different from our linear algebra. See, operator algebra is different. There is an additional term of t square by 2 commutator a b, right? Now let us consider some special cases. Case 1. If t value, the parameter value is equal to 1, then what we will get? We will get e raised to a, e raised to b is equal to e raised to a plus b plus 1 by 2 commutator a b. And case 2. If commutator a b is equal to 0, that is operator ab is equal to operator ba. So what we will get? We will get e raised to a, e raised to b is equal to e raised to a plus b. So now it is similar to algebra, right? Operator algebra become algebra only if this is satisfying ab equal to ba. I already told you one example, that is a plus b or square, right? That is, in algebra it is a square plus 2ab plus b square. But if it is in operator algebra, that is a cap plus b cap all square. I told you this is equal to a cap plus b cap into a cap plus b cap. So when expanding, we will get a cap plus a cap b cap plus b cap a cap plus b cap b cap, right? So if a cap b cap and b cap a cap are same, then we can say it is 2ab, right? That is this one. That means if a, that is here, it is a b is equal to ba. But in quantum mechanics, this ab, that is operator ab, in most of the cases is not equal to ba. And I told you one example also. What is it? X cap px cap is not equal to px cap x cap. Okay. So remember this equation, because this is the most general equation. So by substituting these values t equal to 1 or this condition commutator ab equal to 0, you can derive all the other equation. So remember this general formula. Now let us discuss some examples. First example, find e raised to x cap, e raised to p x cap. So which formula we will use? Yeah, just now we derived the formula, that is this is equal to e raised to x cap plus p x cap. This is our ordinary algebra. Now we are dealing with the operator algebra, so there will be an additional term, that is plus t by 2. Here t value is equal to 1, so 1 by 2 commutator x cap p x cap. What is this commutator x cap p x cap? That is equal to I h cross. That is, we get this is equal to e raised to x cap plus px cap plus I h cross by 2. Okay, this is the answer. Now, second example problem. E raised to x cap square, e raised to p x cap square. So, use the earlier equation, that is e raised to x cap square plus p x cap square. Now, this much is ordinary algebra, but we are dealing operator algebra, so there will be additional time plus 1 by 2. Here t also 1. Okay, so that is 1 by 2 commutator x cap square comma p x cap square. We already find out this value, commutator of x cap square p x cap square, that is equal to 2i h cross into x cap p x cap plus p x cap x cap, right? So this is equal to e raised to x cap square plus p x cap square plus 1 by 2 and 2 will cancels, remaining I h cross x cap p x cap plus p x cap x cap. Okay. Initially, I tell you the value of this one, that is e raised to a b e raised to minus a cap is equal to b cap plus a cap b cap plus 1 by 2 factorial a cap commutator ab plus 1 by 3 factorial into commutator a commutator ab plus etc etc etc. So this will be the value. So we are going to do the derivation. Then only you will get an idea how this will come. So let us consider a function f of lambda, that is e raised to lambda a b e raised to minus lambda a. Now I am going to find out a derivative, that is df of lambda with respect to lambda, that is I am representing this as f dash of lambda, that is equal to, see, it's a product of 3 terms. So first we can take the derivative of first term, that is e raised to lambda a cap, derivative of lambda a cap with respect to lambda, that is a cap b cap e raised to minus lambda a cap. Now we can take the derivative of second term. See, in b there is no lambda, so we don't want to take a derivative with respect to b. If you take, it become 0. Okay, so the last term is minus, because there is a minus lambda a. So here I am writing this minus, or leave it, we can write plus. So we can take the derivative of this function, right? That is e raised to lambda a b cap. Derivative of this function is e raised to minus lambda a into minus a, right? Minus a. Okay, that minus I am taking here, right? So I can write this as, see, ab minus ba. The other terms are same. So e raised to lambda a into commutator or some bracket ab minus ba. I'm taking this as bracket, just a bracket. Okay, into e raised to minus lambda a. See, what is this ab minus ba? We can represent this as a commutator ab, right? That is, this is equal to, that is f dash of lambda is equal to e raised to lambda a into commutator a b into e raised to minus lambda a cap. Now again I am going to take its derivative, that is d square f of lambda by d lambda square that I am representing as f double dash of lambda. So we have to take derivative of this function. So what we get? We have to take derivative of first function, that is e raised to lambda a. Derivative of lambda a is with respect to lambda is a into commutator ab e raised to minus lambda a. Now we have to take derivative of second time, right? That is minus e raised to lambda a commutator a b e raised to lambda a, and there is a derivative of this function, so we will get a minus a. So that minus I put here, and a e raised to minus lambda a. Here also there is a common term, that is this one is common terms in both condition. So I am taking this e raised to lambda a into a cap into commutator a cap b cap minus commutator a b into a cap into e raised to minus lambda a cap. So what is this one? This is nothing but commutator of a with the commutator ab. See, first a into commutator minus this term into a, right? That is this one. That is equal to, we got f double dash of lambda is equal to e raised to lambda a into commutator a cap comma commutator ab. Similarly, if you solve for f triple dash of lambda, you will get this is equal to, see I missed one time here, there is minus lambda a. So if you take third derivative of this function, you will get e raised to lambda a into a commutator ab into e raised to minus lambda a. Here what is our interest? Our interest is to find out f of lambda. What is f of lambda? That is equal to e raised to lambda a b e raised to lambda a. So from this values of derivative, how we can find out f of lambda? That is nothing but Taylor series. That is the idea of Taylor series is, if you know the value of a function at a particular position and you know all its derivative, then you can find out that function. That is, the idea is, if you know the value of a function, the particular value of a function at a particular point and all derivatives, that is, you know there is a function, some function is there, okay, and for this function at a particular point, that is if lambda equal to 0, so suppose this is the function, then lambda equal to 0 means suppose this is the point, and if you know this point and all the derivative, that is you know f of 0 and you know all the derivative at this point, that is f dash of 0, f double dash of 0 and all. So you know only about this point, right? That point and all its derivative. Then you can find out this entire function. That is the idea of Taylor series. Here we found all the derivative of this function. So by using Taylor series expansion, we can find out that function. Okay, that is what we are going to do here. What is this Taylor series? That is Taylor series of, we are dealing with a function which is function of lambda at lambda equal to 0. Then we can find out this function, that is f of lambda, that is equal to f of 0 plus lambda minus 0 by 1 factorial f dash of 0 plus lambda minus 0 all square by 2 factorial f double dash of 0 plus lambda minus 0 all cube by 3 factorial f triple dash of 0 plus etc etc. See, here we know f of lambda e raised to lambda a b e raised to minus lambda a. So we can find out the value of f of 0, that is we have to substitute 0 for lambda. So e raised to 0, that is 1, so we will get b. And earlier we found f dash, that is equal to e raised to lambda a ab e raised to minus lambda a. So we can find out f dash of 0, that is equal to e raised to lambda a, that is 0, right? So e raised to 0 is 1, that is ab. And we know f double dash of lambda, that is equal to e raised to lambda a commutator a ab into e raised to minus lambda a. So here also we can find out f double dash of 0, that is equal to commutator a ab, right? So we can substitute all these values in this equation. So f of lambda is equal to, that is f of lambda is e raised to lambda a b e raised to minus lambda a is equal to f of 0, that is b, plus f dash of 0, that is lambda into f dash of 0, that is lambda by 1 factorial into f dash of 0 is commutator ab, plus lambda square by 2 factorial into f double dash of 0, that is a into ab. Similarly, you will get the another term, next term, that is lambda cube by 3 factorial a commutator a commutator a b. So this is the answer. It's not ended, plus etc etc etc. Okay. So this is what I told you in the first. Okay, it is not difficult to remember. Just remember the Taylor series, relate with the Taylor series. So b is in the middle position, write it here. Then lambda by 1 factorial commutator of ab. Then there is a commutator ab is there. Additionally, one a is added. Then lambda cube by 3 factorial. Here commutator of ab is there. See, same thing. A is there. One more a is added. Okay, nothing else. Okay, please remember this. Okay. This one is a very general formula, so we can consider some special case. What is special case? Lambda is equal to 1. So if lambda is equal to 1, what we will get? We will get e raised to a b e raised to a minus a is equal to b plus ab plus 1 by 2 a comma ab plus 1 by 3 factorial, that is 6 into a comma commutator a commutator ab plus etc etc etc. Okay. So remember this one or remember the general formula. If some little difficult questions are asked in exam, then you can use this general formula and you can find out the exact answer. And most of the cases, this equation will be sufficient. Okay.